Good day, I'm Norman Wildberger. Today we're looking at propositional logic and inference rules, and I want to show you how the Algebra of Boole is a powerful technology to help us understand inference rules and to prove them, and later on perhaps even to transcend them altogether. So propositional logic originates with the work of the ancient Greeks, typically Aristotle and the Stoics. And the aim was, of course, to systematize reasoning, to provide cut and dried methods of being able to structure arguments to decisively get at conclusions. Now, the kind of standard form that one sees in most propositional logic courses for an argument is to start with a certain number of premises. And these are premises, these are things that we assume, that we are holding that they are true, and then we're moving towards establishing a conclusion. That's the basic structure. So sometimes it's laid out like this with premise 1, premise 2, premise 3, etc., and then a bar, and then the conclusion underneath. Or sometimes we could make it more algebraic by stringing these premises together and taking P1 and P2 and P3 implies the conclusion. Okay, when we think about it this way, then we have an algebraic expression that can be encoded using the Algebra of Boole, and then showing the validity of the argument amounts to establishing that this proposition is actually a tautology, namely that it's always true in the context of propositional logic, but in the context of the Algebra of Boole, it would be to show that it's always equal to 1. Because when we go from propositional logic to the Algebra of Boole, we are mathematizing things. We're replacing true and false with 1 and 0, making it much more arithmetical and tight. Okay, so now in order to be able to do this kind of argument, inference rules are very useful. So we're going to have a look at some of the simpler ones today, and I'll leave a few of the other ones to the course itself. So the most well-known inference rule is Modus Ponens, which is the following. We assume a statement P, and we assume that P implies Q, where Q is another statement. From these two premises, we deduce Q. For example, if P is it is raining, and Q is I get wet, then the premises would be it is raining, and if it's raining, then I get wet. Conclusion from those two, I get wet. Now we can rewrite that as a single proposition, combining the two premises into one by taking an and. P implies Q, and then the conclusion is Q. So we write it as P times P implies Q, implies Q. And I remind you that the precedence of operations here is, when you see this implication here, it's weaker than this, something like this. So this operation is done first. First we multiply these two things together, and then all of that implies Q. Okay, so natural question is, why does this inference rule work, or why is it valid? So let's prove it using the Algebra of Boole. Let's look at this expression. P and P implies Q implies Q. And what we want to do is we want to translate it by replacing these connectives with simpler expressions just involving the addition and multiplication inherent in the Algebra of Boole. So the product is just a product. So P and this is how we express P implies Q in the Algebra of Boole. P implies Q is the same as 1 plus PQ. So we've rewritten it, first step there, and now we rewrite it further because it has the form of something implies something else. So we write it as, well, first of all, we simplify this something. There's a P times 1, which is P times P, which is also P, and P times PQ, which altogether just amounts to PQ. So this becomes PQ implies Q. Now another implication, we rewrite that as 1 plus the first one, PQ, plus the product, PQ times Q. And since PQ times Q is the same as PQ, and there's two of them there, they cancel, and we just get identically 1. Okay, so the proof of this inference rule in the algebra of Boole is a computation which amounts to taking an expression and evaluating it, finding the Boole polynumber that it's equal to, that it reduces to. And in this case, it reduces to the Boole polynumber 1. So that's the algebra of Boole, equivalent to being always true. It's always equal to 1. So that's the way all of these things kind of work. We have an expression, we simplify it using our grade 9 simplified algebra, and we hope to get 1, which establishes it as a tautology, or as a valid rule that works in all cases. Now the second major inference rule is Modus Tollens. Here are the two premises for that. There's also a P implies Q, but the other premise is not Q. The conclusion of these two is not P. So if P is it is raining and Q is I get wet, then this statement says if it's raining, then I get wet. While this premise says I don't get wet. Conclusion from that, it must not be raining. That's the nature of Modus Tollens. In terms of a statement, a single expression, the two premises are combined with an and then there's an implication of the conclusion. So we get not Q and P implies Q. All of that implies not P. So we take this expression, and to prove it, we are just going to simplify it. That means replacing these various logical connectives with the corresponding expressions in the algebra of Boole, and then simplifying. Okay, so not Q is the same as 1 plus Q. The and is the product. P implies Q is 1 plus P plus PQ. Implies not P is 1 plus P. We simplify this product. Let's see, we multiply by 1, so we get 1 plus PQ, and then we multiply by Q. Q plus PQ plus another PQ. And that simplifies because these two PQs cancel, so we have 1 plus P plus Q plus PQ implies 1 plus P. Okay, so now it's an implication. We rewrite it as 1 plus the first term plus the product of the two terms. Okay, now we have to simplify that. So what happens? 1 plus 1, that's going to disappear. There's a P, there's a Q, there's a PQ. Over here, this 1 plus P times 1 plus P is 1 plus P squared, which is the same as 1 plus P, so that's why we're getting a 1 plus P there. And we still have to multiply Q plus PQ times 1 plus P. So times 1 is Q plus PQ, times P is PQ plus another PQ. And then there's cancellation. Maybe I'll show you what it is. So these two PQs cancel. Here's a PQ and there's another one there. They cancel. The two Qs here cancel. The two P's cancel. And all that's left is this single 1. So this computation, which is really just a simplification or a reduction, that establishes that Modus Tollens is a valid inference rule. Another very important inference rule is the hypothetical syllogism, which we've already talked about. P implies Q and Q implies R. From those two premises, we can deduce that P implies R. Here's another one called disjunctive syllogism. P or Q, not P, therefore Q. If P or Q is true, one of those two is true, at least, because it's an inclusive or. But we also know that P is not true, then it has to be that Q is true. Now, remember, however, when we convert to the algebra of Boole, we're not primarily thinking about truths and falses. We've made this shift to zeros and ones. These are no longer English statements that have possible truth or false values. They are rather elements in a Boole algebra which we can operate with the laws of modulo 2 operations. Okay, so to convert it, we take the product of the premises, P or Q, times 1 plus P, and that implies Q. So we're going to rewrite this thing. Okay, P or Q, right? That's an inclusive OR. To rewrite it in the language of the algebra of Boole, it's P plus Q plus the product PQ. Times 1 plus P implies Q. Expanding this out, what do we get? Okay, P times 1 plus P is 0. Q times 1 plus P, well, there's a Q, there's a QP, and PQ times this is also PQ and another PQ. Well, there's some cancellation here. We just have Q plus PQ implies Q. Now this implication can then be replaced with 1 plus the first term plus the product of the first term times the second. And the Q squared here is a Q, which cancels with that Q. And the PQ times Q is a PQ, which cancels with that PQ. And we're left with just 1. This is really a nice application of algebra. So if a grade 9 student has learned some manipulation with polynomials, how to do algebra, then this is, I think, an attractive kind of application. A grade 9 student could appreciate that they have some power here. This fiddling around with polynomials in this very simplified way, because everything is mod 2 reduced. We get to rub off powers whenever they appear. We get to just remove anything that has a factor of 2 or any even number in it. That's great. That's simplified. That algebra is enough to establish, pretty simply, all of these inference rules. It's a very attractive application that maybe high school students might want to see. Here's a slightly more sophisticated inference rule called resolution. P or Q is one of the premises. Not P or R is the second premise. And the conclusion is Q or R. So as a single statement, we have P or Q times not P or R implies Q or R. Okay, so let's see what happens. P or Q, that's P plus Q plus PQ. Not P is 1 plus P. So this is 1 plus P plus R plus the product 1 plus P times R. And implies this OR, which is Q plus R plus QR. Now this thing simplifies a little bit. We've copied this here, and over here we have a 1 plus P. The R's cancel, and we have a plus a PR. Implies the same thing over here. Okay, when we expand this out, let's see, we get a P times 1 plus P, that's 0 as always. We get a Q, a QP, and this PR times P will be there. The PR times Q, the PR times PQ, they will cancel, so we'll just have these three terms. Implies Q plus R plus QR. Okay, so now it's a single implication. That's equal to 1 plus the first term plus the product of the two terms. Now we have to simplify all of that. Okay, let me try to do it here. So what cancels? So this Q is going to cancel with one of the products here. Maybe I'll write it like this. Q times Q. That Q times Q is going to cancel with that Q. This QP is going to cancel with this QP times that Q. They'll cancel. This PR cancels with this PR and this R. Okay, what have we not taken account of here? We still have a Q times PR, Q times PR, and that will cancel with this QP times QR, which will also be a QPR, so that will cancel with that one. What else have we not done yet? This R, we multiplied it by this one. If we multiply R Q, so there's an RQ. Where is that RQ? this R with this Q. Okay, yes, okay, this R with this Q, that one there, that's a QR. That's also going to appearing here with this Q times that QR. Okay, so there's two emerging here, one there and one there. So I still have to have Q times QR. Oh no, I've got that one up there. Okay, that's already done. This one here has two coming out. There's one more, I guess QP times R. We haven't done that one yet, so let's do that one. There we go. And oh, we still have to do this one here. And those are both QPRs, so they cancel. Okay, maybe it's a bit lazy doing it this way, but we could just easily expand it and cancel things out. But the point is that at the end of it, we get everything cancels except for 1. So our grade 9 algebra suffices again to prove this inference rule. Okay, so now we're in possession of at least some useful inference rules. Let's go back to a puzzle I showed you some videos ago about about poetry and soap bubbles and interesting and popular, etc. It's from Lewis Carroll's collection, and here are sort of a summary description of what's that about. So we introduced some phrases, some sort of atomic phrases or propositions. I stands for it is interesting. M stands for it is modern. Y stands for it is your poem. P for it is popular. A for it is affected. And S, it's about soap bubbles. And then the puzzle consisted of 5 statements, and I've translated those statements now in terms of connections between these 6 relations. So the first one was I implies P. If it's interesting, then it's popular. M implies A. If it's modern, then it's affected. Y implies S. If it's your poem, then it's about soap bubbles. A implies not P. If it's affected, then it's not popular. And finally, not M implies not S. If it's not modern, then it's not about soap bubbles. And I asked you at that time to see if you could come up with any interesting conclusions to these various premises. Now, in fact, in this generality, we expect that there's lots of conclusions that we could draw. Okay, there's lots of conclusions. But we're looking for kind of a simple conclusion that's easily stated. And this happens to be the main conclusion, which is a little bit painful, because it says Y implies not I. In other words, if it's your poem, then it's not interesting. The conclusion is that your poetry, sadly, is not interesting. So we would like to see how we can establish this logically using our inference rules. To make that a little bit smoother, I want to introduce a clever little technique that allows us to prove implications a little bit more smoothly sometimes. So this is actually an identity. It's not really an inference rule, but it's an identity of expressions. It's saying that this expression is the same as this expression. This one is P and Q implies R. And this one is P implies Q implies R. So these are both expressions. They both can be simplified and reduced using the Algebra of Boole. And the claim is that what we end up getting is the same. These are the same Boole polynumbers. So let's have a look at the first one. P and Q implies R. Well, P and Q is the same as P times Q, so it's P times Q implies R, which is 1 plus PQ plus the product PQR. The second one over here, P implies Q implies R. That's P implies 1 plus Q plus QR. And then this is going to be 1 plus P plus the product P times 1 plus Q plus QR. And then when we expand this, the P times 1 there will cancel with that P. We'll have 1 plus PQ plus PQR, which is the same as we got up here. So these things are actually identical. We could say something weaker. We could say, this implies this. That would also be true in the sense of being a tautology. So we could put an arrow like this. We could also put an arrow like this. That would also be a tautology. But the equality here is stronger. It's telling us these things don't just, imply one implying the other. These are actually equal. Okay, so that means whenever we have something like this, we can replace it with something like this or vice versa. All right, so let's get back to your poetry as analyzed by Lewis Carroll. Here are the 5 statements or premises that we've already talked about involving the shortcuts that we've established. And we want to deduce from this that y implies not I. So what we're going to do is we're going to use that previous identity and augment the premises with y. So all of this and y, if we can prove that implies not I, then that's the same as saying that these first 5 premises implies y implies not I. So this is a useful technique when we're trying to deduce something which is itself an implication. In this case, y implies not I. We take the y out and make it a new premise, add it to the list of premises. Roughly speaking, the more premises that we have, the more options we have for manipulating things. Okay, so we now have 6 premises. We label them 1 through 6. And now we look around for some deductions. Okay, so let's have a look at 3 and 6. Here we have y, and here we have y implies s. Well, that's just what we need to apply Modus Ponens. If we know y, and we know y implies s, then we deduce s. So that's Modus Ponens using 3 and 6. Okay, now we're going to use 5 and 7. So 7 is the one we've just established, namely s. And 5 is over here. So not m implies not s. But we also know s. Now s is the not of not s. Not s is the same as s. So when we were talking about Modus Tollens, we had not q together with p implies q. From that we deduce not p. So it's the same kind of thing here. From s and not m implies not s, we must deduce not m. Not m is the same as m. So that's Modus Tollens applying to 5 and 7. We can call that 8. Now let's go up here. We have m now. Well, over here this m implies a, so we can deduce a. That's Modus Ponens from 2 and 8. Now that we have a, we can establish not p. That's again Modus Ponens using 4 and the one we just established, number 9. So we have not p. Here we have I implies p. If I implies p together with not p, we deduce not I. That's Modus Tollens with 1 and 10. That's the one that we are interested in. Okay, that's the one that we want. So now we can deduce that these first 5 things, which I have written them together as a product, that whole thing, implies y implies not I. So if these 5 things are true, namely if Lewis Carroll's statements are true, which none of us can argue with, then it must follow that your poetry is necessarily uninteresting. And of course, I'm sorry about that. Okay, so that's fun, clearly. But there's a few things to say. Okay. One of them is that we are making this transition from statements about the real world involving notions like poetry and popular and interesting and so on, into this mathematical framework, which we're modeling as just vectors with zeros and ones. So the validity of that transference, the validity of the application going from the real world to this mathematical modeling is maybe questionable. So it's not automatically obvious why that should be entirely valid. The other point to make is that you can kind of see in this example that it's been carefully constructed by Lewis Carroll, who was quite good at these things, to have a nice clean path through it, right? We found a relatively simple argument just using a few relatively simple inference rules. But what would happen if we had a much more complicated situation? What would happen if we were not talking about some cute little puzzle involving some poetry and such, but rather maybe a large system with all kinds of relations that perhaps models some important real-life situation? Maybe an automatic system for controlling driverless cars in a city. There might be all kinds of rules that we establish, maybe dozens or hundreds of rules, and we might be interested in whether these rules imply certain other ones. So with such a bigger example, we can't expect that there's going to be some clean, clever way of getting particular deductions. So we really are looking ultimately, if we want to go beyond just sort of elementary courses, we are looking for a more powerful general technology. Okay, so we're going to be moving towards that, and we're going to see the algebra of Boole is a very important ingredient in that, but we're going to have to also introduce some more modern algebra. But before we do that, I want to talk about something that just came up briefly today, which was that identity that I showed you. So there are other identities that are worth pointing out. So aside from the inference rules of propositional logic, there are also certain useful identities that it's useful to lay out so that we can see them clearly and apply them also in situations. But ultimately, we do want to think about how to transcend this ultimately sort of elementary technology to empower us for bigger situations and bigger and more complicated situations. So lots to move forward towards. So I hope you'll join me for that. I'm Wildberger. Thanks for listening.